Okay, so this section needs to have very clear mind because this is very important in every data publication. We're talking about quality control, statistical analysis, and result viewing, especially the statistical analysis part. So once we use the part of the Excel to perform the processing, we have the method, we have AFF, we have numerical, we have function maps. Then we need to do quality control, select those subjects and group quality, and then perform statistical analysis, and then build the results. So for quality control, in Hipagi we have a quality control module, and once you click the quality control, you have this graphic user interface, and that has lots of buttons. And for example, you can quality control the raw T1 data, for raw function data, for nummerization, for quality control score, for generate group masks, threshold coverage, and check the motion and threshold motion. And firstly, you just tell the program what is the working directory and what the start directory to load the subjects. And the QC row T1, once you click that one, it will pop out that you have give this subject a score at the lowest step. And the score maybe is 5, and you give a comment, very good. And then you click the view button, it will just call the subject's T1 image data jump out for you. And then you can view the data and just try to remember why I gave these subjects a very low value, very low quality control value, and you can check if there is something wrong with the data. And you can also check in another way, in quality control directory, there's a raw T1 image qc.tsv. You can use Excel to open that file, and you can see this subject ID, and you can see the quality control score, and then QC command, and you can change the quality control score if you like, and then later we can use that. For function data, it's all the same. Just check the quality control and check the score. And this is the quality control for normalization. So for normalization, if the first time to click this button, it will pump out for the spatial quality control. So at the top left, this is normalized T1 data, and the top right is normalized functional data, and the bottom left is normalized gray matter data, and the bottom right is MI template. And all the images you can see the yellow lines. The yellow lines is the MI space, the boundary between gray matter, white matter, and the gray matter at the same time. So you can see if the yellow border fits to your data. If fits, then the spatial normalization is good, and you can give a quality control score and give a comment if the data is good or not. And if the second time to click the quality control normalization, you can see the table. So what you have give, the quality control score and comment. And then you can also open the normalization qc.tsv, and there is also Excel file. You can see the data and how did you give the quality control comments. And another way to check quality control is in the pictures for check normalization folder, they have lots of subjects. They have the picture files, and you can just open those picture files to see, for example, if the underlay, the white one is normalized function data, and the overlay top one is structure data. If they fit together, you can use that as a quality control way. And you can stretch the QC score. So here, it will tell you can set up the threshold. So for example, it says 3, then all the quality control scores less than 3, they should be removed. Those subjects will be removed from the subject list. And this is generate group masks. So we talked about in this morning that we will generate auto masks. So for the auto mask, that for subject in the auto mask, this is a spatial coverage of the functional data. And the doublet automask means that automask in unmatched space. And use this one, we can create a group mask to see how many subjects overlap this voxel. And we can give a threshold. For example, we give a 90%. So that means 90% of the subjects covered this voxel we are included into a group mask and use that for statistical analysis. It will give you a group mask 90%. So this one is very important for group statistical analysis. And we can also threshold coverage. So once we have the group mask, we can select the group mask, and for those subjects have very few overlap with the group mask, you can exclude those subjects. And this motion report, you click motion, and you can see different subjects have the mean FD values. This mean FD Jackson, you click view, you can see the time series. Then importantly, you can threshold motion. You click this one, it will tell you the mean FD Jackson, the group mean is how much and the standard deviation. So usually you can use the threshold 0.2, or you can use a mean plus 2 SDs. And this is most quality control comes through our literature paper onto the standardizing the intrinsic brain towards robust measurement of individual variation in 1,000 function connectors. This paper is also 1% top highly cited paper. And once you have done the quality control, you have selected those subjects have good quality of imaging, and then you can perform statistical analysis. So in part we provided a statistical analysis module, and for this statistical analysis module, this also works for the surface-based data. And for statistical analysis, you can perform different kind of statistical analysis, and you click the drop-off menu. You can perform one sample t-test, you can perform two sample t-tests, you can perform parallel t-tests, you can perform ANCOVA or ANCOVA repeated methods. You can also do correlation analysis or do mixed effect analysis. So basically, these kind of models can cover all you need for most of your analysis. So let's see, this is one sample t-test. One sample t-test will tell us how the method looks like. For example, this is AFF map for the Alzheimer's disease group. This is the AFF map for controls. So it looks like that controls have stronger value than Alzheimer's disease. But keep in mind, one sample test can never give that conclusion. They can only visually inspect how the pattern is. If you really want to see if our Alzheimer's disease have less value than normal controls, you should perform two sample tests. So for one sample test, you just select one sample test, and you organize all the subjects into one folder. So what you need to do is click add and add all the subjects that's in the same folder. So you do not need to add the single files, you just add a folder. Within that folder, you have all the subjects. For example, it will be detected as 16 images, 16 subjects in that folder. And you can set up a base. Most of the times, we perform one test, compound values. If this have a mean of 0, you can also compound with the 1. But most times we compound either with the 0. And you can give a mask, usually this is a group mask, and the output directory, you can get a T image. And later we can use dependent viewer to view the results. Mostly we are using two sample t-tests. I think most of you use two sample t-tests because you have a patient group, you have a control group, you want to compound the two groups, or you have children, you have adults, you compile the two groups. And here, so we look at this kind of paper. So this is performed two sample t-tests between Alzheimer's disease and healthy controls, and they have found the differences within the posterior cingulate cortex. And this we can perform in the DeepIB statistical analysis. So for example, here we can use add, because these two groups we need to add twice. First add the first group, and then add the second group. So the first group has 16 subjects, and the second group has 22 subjects. So we add up them, and we can calculate the t-test. So the t-test, the t-value, you always keep in mind, the positive values means the first group bigger than the second group. And the negative values means the first group less than the second group. And also importantly, we add covariance. For example, in Alzheimer's disease, they have structure change, they have atrophy, and you can use grammatical density as a covariate to control this kind of effect. So you give the covariate images. For example, grammatical density, you add, but just keep in mind the correspondence of these group images is the same. The order is same like here, and also they have the same box size. But usually your function data is 3 by 3 by 3, but the grammatical density is 1.5 by 1.5 by 1.5. So you need to use DPyB utilities image reslicer to reslice the structure images to the resolution of the function image. And here you can add the covariance. So mostly when we compile two groups, you will tell the reviewers, I control the age, I control the sex, and I control the head motion. So in that case, if you want to control head motion, age, and sex, you need, for the AD group has a text file, for the NC group has a text file. So in the text file, so each line is, each row is a subject's covariance. For example, the first row is subject 1, and the second row is subject 2, and you can have several columns. Each column is a covariate. The first column is head motion, the second column is age, the third column is sex. So if you have more covariates, you can add more columns in that text file. And we can also perform parity tests. So nowadays, the two sample test, we need to increase sample size because the Chen Xiao study has showed if you have too small sample size, the result is not trustworthy for the between group design. But somehow, for within subgroup, within group design, like the test retest or the before treatment and after treatment, this one as open as closed, this has much larger effect size and has much more reproducibility. And this is as open and as closed. We use as closed to subject the as open. So, for example, if you use the treatment, you can use the before treatment and after treatment and test if there is a significant change. So this is parity test. And here, what you need to do is add the first group at the condition 1 and add the condition 2, and the t-values is equals to the condition 1 minus condition 2. You have the scores. And you can also give the prefix, and you have the t-statistical images. Mostly for parity tests, we do not need to use covariance because parity tests already control inter-subject variations. But the one thing you can take as covariance is head motion, because head motion in the pre-test they have a head motion, in the post-test they have a different head motion. You can use the head motion as a covariance here. And we can also perform ANOVA and COVA. So that is, if we have several groups, for example, we have AD, we have MCI, we have control. So we have 3 groups. So maybe you would like to perform ANOVA analysis that you see if there is probably there is some difference between any groups, and you can find those areas and do post-hoc analysis. So this case is we have AD, we have MCI, we have control. We want to compare 3 groups. We can perform an ANOVA analysis, and we can see these areas show differences between at least 2 groups, and we can extract the values and see which 2 groups show the differences. So here is in ANOVA, you just add the groups. You click add 3 groups. And you can also use a covariance like a grammatical density and you can also add the text covariance like age, sex, and hand motion. They're almost the same, but only the difference is the result and ANCOVA is app text. And this aesthetic image, and you can perform multiple comparative correction on that. And the one more thing is, usually what we do is we first perform ANCOVA, and we found the significant clusters. We know that at least two groups have significant difference. So then we perform the post-hoc analysis to find out which two groups show the differences. So this kind of is some kind of LSD, and you can use also other multi-comparison correction methods. You can use Turkey-Kramer or Bafroni or Dan-Siddhartha or Scheffer. You can use this kind of different multiple comparison methods to control that. And then what you will have is, this is the app test image. This is the ANOVA app. And this pairwise diff is a difference of mean between two groups. And this p-value after the multiple comparison correction. The most important what you will use is a Z map. The Z map is Z values. And you can see for the first group minus the second group, first group minus third group, and the second group minus third group. And all these maps are after multiple comparative correction. And for these maps, you can further perform the Gaussian random field serial correction, and you have the differences between any two groups. And you can also do the correlation analysis. So the correlation analysis is, once you have a measure of the behavior, for example, MMC in Alzheimer's disease, and you want to see if there is any correlation between the brain and this kind of behavior measure. So we can see the MMC has a value correlated with this kind of brain. So we can use a correlation analysis module. So you do correlation, and you add a group of images. So this is all the subjects. And you also need to add a seed. So seed test series is, for example, your interest, for example, MLC. And you can also add the covariates or test covariates. Then this will perform partial correlation. The partial correlation control the covariates, control the test covariates, and between the brain and between the behavior. So this is what you can control. And finally, it's a correlation map. If you control the covariates, there is a partial correlation map. And finally, we can do the mixed effect analysis. So mixed effect analysis is also very common. Is, for example, this is rice. So rice have adolescent and adult. So from adolescent and adults, they have a development effect. But one group of rice, they have maltreated, and another is control. So what we found is, for the control group, they have a development effect. But for maltreated, the development is stopped. So then this kind of effect, maybe you will be interested to figure out your treatment for the group, will that change the development. So this is a mixed effect analysis that have the between subject effect and within subject factor. So between subject factor is control and maltreated. And then within subject factor is adolescent to adult, is a development part. So you can think about, for your study, maybe you also have this kind of effects. And what we need to do is we need to add the different group and different condition in this way. For example, group 1, condition 1, group 1, condition 2, and group 2, condition 1, and group 2, condition 2, in this order. This is important. Only you add in this order, we can have the interactions between group effects and condition effects. And you can also, more basically, we not add the covariant images because for the interaction effect, you already control that. And for the text covariates, usually you add time motion because time motion is different from the before test and the pre-test and post-test. You've got the mixed effect analysis, and the results, you will have the conditional effect, T. This is a conditional effect. So that means no matter what kind of treatment you have used, they have a development effect. So this is within inside the vector. And we also have a group 2T. So this is no matter what development. That's the difference between the two groups. But mostly you will be interested in the interaction F values. So the interaction means you have a treatment effect between the two groups. They have a different development trajectory, and you can pull out those interaction significant clusters and extract the values, and then plot for the simple effect analysis to see which kind of group show the different trajectories. And actually, all the analysis, I wrote a code called the wide group analysis image. So if you have your own model, you can call the wide group analysis image to get the results. And also, we will estimate the smoothness of the image based on the 4D residual in this group analysis. And there's one need to caution is we cannot use the smooth kernel in the preprocessing to do alpha sim or to do GRF. For example, the ALF, the applied kernel is preprocessing to 4, but on the final image is almost 7. And in Remo, this is even bigger. So preprocessing to 4, but afterwards it's almost 10. So you cannot use a preprocessing kernel for alpha sim. And also, you can look online to check those Wikipedia or to see if you have your own model, you want to set up a regression model, how to set up the regressors. So you can look at this kind of different modules, different regression modules for the analysis, and you can just look at it. If you do not want to understand, just use the modules in the statistical analysis. That should be enough. And the one important thing here is multiple comparative correction. So multiple comparative correction nowadays is very critical because this paper by Acklin et al. They're talking about cluster failure, where my inferences for spatial accent have inflated false positive rates. And after this paper, there's lots of people followed and said the last 15 years of our research might be totally useless. And although afterwards they have a correction on PNX, they changed 40,000 album studies to a number of album studies. And because they have that on their website, okay, said, okay, maybe you made something wrong in the paper. But this is talking about false positive rate, but they have a false positive in the paper. So that is kind of embarrassing. But let's look at what's the problem. The problem is, if we have a test, we set p-value 0.05, what does that mean? It means the probability of not get a false positive result is 0.95. And another task or another voxel, you set p 0.05, not getting a false positive result is 0.95. And all the voxels you have set p 0.05, they all do not have false positive results is 0.95. And you combine the 5 voxels together. So if you have some knowledge of the probability, then you will know you will not have a false positive. It's 0.774. So you have a 20% at least to have a false positive. So that's not acceptable. So that means if you do not do correction, you scan the brain, you will always have results. So this is why people like to do brain image studies, because they just collect some data, scan some subject, they always have papers, they always have results. But a long time ago, people already know this, because one guy scanned a dead sample, a dead fish in the scanner, and got activation in the dead fish brain. And so that's worrying. And people know we need to do something about that. So one thing is to Bartholin correction. So Bartholin correction is if you set p-value 0.05 at the end, you just use, if you have 5 voxels, you just use 0.05 divided by 5. So for each voxel, you have to set up 0.01. However, there will be a problem. Then nobody will do functional imaging because we have tens of thousands of voxels in the brain. If you want to do Bartholin correction, then you should decide individual 0.00 to the minus 0 to the 1. Then you will have no result. Maybe in the future we need to Bartholin correction, like days ago we have an international conference on brain imaging of depression. They are talking big data. Maybe in the future we have tens of thousands of subjects. Then you can perform Bartholin correction, but no. Then there are some other corrections, like the false discovery rate correction or family-wise error rate correction. But family-wise error rate correction is not a very exact term, because within the family-wise error rate correction, they all have Bartholin correction, Gaussian random field series correction, Monte Carlo simulation, threshold-free clustering alignment, and permutation tests. All can control the family-wise error rate. Let's first look at the false discovery rate correction, FDR. So what is false discovery rate? So if we have two non-hypotheses, that means the two groups really do not have a difference. And if you declare that's significant, then you made a false. And this non-true non-hypothesis means they do have a difference, in fact. And if you declare significant, you got a hit. This is a true thing. So what here is, after you test, you declare that 100 voxels are significant. And here is V is there are 5 voxels. They really do not have the differences. So this is a false discovery. And the false discovery rate is V divided by R. So that means if you declare that 100 voxels are significant, there should be no more than 5 voxels are false discovery. That's control the false discovery rate. So the FDR correction, you can just sort the data and find the correct p-value, and that is the data is our FDR correction. But usually we do not use FDR correction in the whole brain data. Mostly we use that in the network analysis. For example, we have lots of nodes, we have lots of connections, we perform FDR correction. And if you want to perform FDR correction in hepatic view, and you can just click the cluster and click the FDR correction, and then just tell it, well, it's a mask file. So why is a mask file important? It's because if the search volume is bigger, then the correction is stricter. So that means if you have a hypothesis that you find differences in hippocampus, then you set a mask at the hippocampus, very likely you can find some results. However, if you do not have a hypothesis, you can set up a whole brain, then the correction is more strict. And you can set up the Q value. So after control, what the false discovery rate will be. And then compute, you can get the results. And another way is Gaussian random field serial correction and Monte Carlo simulations. The general idea is almost the same. It's just, for example, if we set up a threshold, if you cut P at 0.01, then there are some voxels left like this. Or if you set up P smaller than 0.01, then the voxels left like this. Which one you think will be more random? Left one. So left one you think is more random, This is very intuitive. So actually, you can do that. You can do randomizations. So we do randomization and cut p-value 0.01 and see the biggest cluster they can connect. And have another randomization and cut p0.01 and see how big the cluster will be. And then finally, you can have all the results. And if you found in your real data a cluster bigger than the random biggest cluster, then you can declare this is not a random effect. Although in the randomization we should consider the smoothness. So that's why we need to give a smoothness parameter. So that in the image we have a randomization, we smooth the data as a brain, and we detect what's the biggest cluster in the random data. So Gaussian random field theory correction is they develop a formula. If you tell me the smoothness, I can tell you at random what the biggest cluster will be. And the Monte Carlo simulations are the same, just to do the randomization. So what you need to do is you have view the cluster, and you use GIF, and you tell it what's a mask file. So usually your group mask. And if you do not have, you can use all templates, grid mask, 05, 61, 73, 61. These are default masks. And if you use DeParby to perform statistical analysis, then we will automatically estimate the smoothness based on the 4D residual of the data. If not, then you can estimate the smoothness on the statistical image directly. Then that will also estimate the smoothness. And then you give the box p-value and the cluster p-value. And nowadays, if you want the reviewer to have no issues with the statistical analysis, the box p-value should be 0.001, 0.001. And the cluster p-value is 0.05. And more importantly, if you are also interested in the patient bigger than control, and patients less than controls, then you need to click the two tails and compute and hope you will have some results still. For upper sim, the difference is you need to tell it the iterations, how many simulations you want to do, and what's the box p-value. Nowadays, the box p-value should be 0.001. And after that, it will do a simulation and give you a table. So in the table, you need to find out. So for example, alpha, the first one smaller than 0.05 is this one, and the corresponding cluster size. You set up the cluster size in DeParby view that this upper sim corrected. But we no longer that we normally use a GIF correction. And this is a TFCE, threshold-free cluster enhancement. So basically, use some. Basically, the idea is this. So here the voxel has very high t-value, but its neighbors have very low. Then just keep it like that. But this voxel not so high, but its neighbors are all very high. Then this will be enhanced. So as those they enhance. So the TFCE has the advantage that in GIF correction, in upper sim correction, we should set up initial threshold like p smaller than 0.001. But here you do not need to, you no longer need to set up the threshold. And if you do not know the distribution of the TFC or of the data, we can use permutation test. For example, we have 100 controls and 100 patients. Just randomly split them, random exam, if this is the control, this is the patients, and you see the results, and you get the distribution. And follow this paper, what they found is here. The initial threshold is very important. If the first threshold, P0.01, they have a big problem. Most of the cases, they have very heavy inflation of a family-wise error rate. Only if you set up the p-value at the initial is 0.001, so you can control the family-wise error rate, or if you use permutation. So this tells us maybe now we should use computation, or we should set up the initial threshold at 0.001. And if you do not do multiple comparison correction, the false positive rate may be 70%. So that results we do not trust. And also, they talk about the alpha sim bug. But the alpha sim group said this is not the bug problem. This is buggy. This is fixed. This is not a problem, but some other issues like the long tail. And often they also use the permutation test we know. And if you use permutation test, then you can control the false positive rates. And this is the Chen Xiao's work. Tomorrow he will explain in more detail. But basically, here, if you use the loose threshold at the beginning, then the false positive rate are very high, the family-wise error rate. And only use a very strict one. If you are into two-tailed, each tail should be 0.0005, and each cluster-wise is 0.025. Or if you use permutation task, or you use FDR correction, this can control the family-wise error rate. And here, we still have too many choices. So another way, okay, this is the numbers for family-wise error rate. And this is all the stuff which can control the family-wise rate. But there are still too many, so we use reproducibility as another way. For example, test retellability. They are scanned for one time and scanned for a second time. So we have the differences. We see the overlap. We use DAS coefficient, and this is DAS coefficient. Seems it's okay for the test retellability. And we also use replicability, and all the answers is permutation test with TFCE. It's a pretty strict multiple comparison correction strategy that reach the best balance between family-wise error rate and test-retest reliability or replicability. So we recommend you to use permutation test with TFCE. And another thing is Chen Xiao's work found the sample size matters a lot. If the sample size is too small, the test retellability are very small, the sensibility is small. So it's very difficult for you to find the significant results, and the positive predicted value are very low. That means even if you find some significant results, they're not reflecting truly fast. This is basically the conclusion from his paper. He will explain more details tomorrow. And in DIPADI, permutation test is very easy to perform now, because before it's pretty difficult to perform. But now, in DIPADI statistical analysis, what you need to do is just click this button, click the permutation test with POM, and this is also integrated the POM, the Winker's POM package. You need to set up the number of permutations. So basically, usually we use 5,000. And you can set up the cluster inference, but basically we do not usually do not use that one, and we mostly use the TFCE. Although you can do FDR, but what we do usually use the TFCE and the two-tail, and we do not need to do the acceleration. And afterwards, you will have lots of files, these temp files and the T2 box T-stat. The T2 box T-stat is a T-maps, which we use a lot. And the TFCE, FWEP, this is the correct p-value, we use that a lot. And here, the box T-stat is the t-value of voxel, and also we have the FWEP is corrected. And afterwards, how you view the results is you open DIPADI viewer and open the T2 voxel T-stat.nr. This is a t-value map, and this is a t-value map. This is uncorrected. How to correct that? We create the cluster, apply a mask for additional threshold, and you find out the T2 TFCE T-stat FWEP.nr. Basically, it's a file with TFCE and FWEP. This is corrected p-value, and you just set up the threshold smaller than 0.05. So the TFCE FWEP file and the smaller than 0.05 and the compute, it will apply the corrections. So after applying corrections, this is the corrected results, and these results are significant. And also, this is just basically to show the funding for the multiple comparison correction. The final part of this talk is results viewing. So once we perform the statistical analysis, we perform the multiple comparison correction, we need to know what the result is. So we can open Ipapi Open Viewer, and this is the viewer. And firstly, you can select underlay. So the underlay is the structured image. You can see how the image looks like, and you can select your own structured image as well. So overlay usually is a function image of the statistical image. So we click the statistical image, we open that, we use that overlay. And also you can add multiple layers. So different layers, you can set up different structural max, mean, and you can set a color bar. You can give the different time points. And here it's threshold. If you drag threshold, the threshold changed. And also if you have a degree of freedom value, you give a p-value, it will convert to a threshold value. And this only positive value or only negative value or none of them, this can give you a direct viewing of the results. And this is XYZ means abstract coordinates of the data. So if you want to see some specific coordinates, you can go there. And IJK is because our data is in MATLAB format. So as it is in MATLAB format, you can use a matrix. So the IJK tells you what's the index of that box. And the A and C means you can see this kind of figures. You click A, Excel, and then you have this kind of figures, and you can put that into your paper. And the cross is have a cross or not, and you can set up 3 rows, 5 columns, beginning from where, and the space is 8 millimeter, and you can apply. You can also click the input matrix. Click the input matrix, you can just type in which slides you want to look at, and you can save it into a figure. So this makes you can make this kind of slices to pictures and make it into your paper. And also we have the controls. This is 100%. You can use that to zoom the picture, and the plus that means if you want the cross or not. And the Y means yoke. If you click Y, click yoke, and you can create new, open another viewer, then the 2 viewers will yoke together. You click anywhere, then another viewer will go there as well. So in that way, you can see the differences between 2 pictures. And the cluster, as we discussed, we can do the multiple comparison corrections. We can set class size. We can save a single cluster. For example, after we perform statistical analysis, perform multiple comparison correction, we have a cluster. We want to extract the values of that cluster, maybe save as a mask for function activity analysis, or just extract the values to plot the values. You just click Save Single Cluster. You can save that cluster to a mask, or you can save all clusters, or you find a peak in the cluster, or you can use the volume percentage, or you can do FDR, GRF, or RC correction. You can try that. And this is what we also discussed about the GRF correction, smoothness, or estimate smoothness, and have box period 0.01, 0.001, and the class period 0.2, 0.05, and get 2 tails. And one more is in the more you can view the temp cost, or you can, if you install the Brunel viewer, you can see the surface view with the Brunel viewer. And in the next version, we have a surface view with the Ipapi surface view with the all own surface viewer. You can set a range threshold. For example, in the data you only want to display 28, average 28. you can set the range threshold 28 to 28. You can set the color bar manually, or set the overlay transparency, or save interfaces as a picture, or save color bar as a picture, or save colors as a matte, or load the color bar as a matte. And then, for example, for time courses, you click this one. For function data, you can move to anywhere and also watch the time courses. So that is very easy for you to check the data. And this is time domain because it's time. If you click this one, it will change the frequency domain, and you can see they have most amplitude and low frequency bands. And the atlas, for the atlas, you can click different atlases, and once you add atlases, you click anywhere, it will tell you where it is. For example, tells you now it is a single jealous posterior division. So it's very easy for you to understand where the signal result is and where is my result, and how can I write the description. And importantly, okay, this is PCC, and found in the literature why PCC should show this kind of difference. And you can also use the structure, and you can overlap the structure, and you can preview that. You can see the results overview with the structure, how they overlap with each other. And you can see also these kind of surface maps. And this is a EL7 network. The surface maps, you can just, for example, use the EL7 networks and set the P-mean value. And this is the default color bar. For EL, the color bar, you need to load the color bar from Might, load the EL color bar for DPI, and basically it just defines for each different values what the color should be. And after you load that, you can see this is different EL regions for the different area. And you can click the surface view with the Brunel viewer, and you can have this kind of view. And finally, again, for protein test with TFCE, you need to do is open the box tstat.ni, and here you open the TFCE FWEP and set the threshold. And threshold is 0.25. And actually, usually we have this kind of data after apply. We will set up the threshold here. 2 is okay, but just or 1 is also okay, just to prevent the 0 values on the surface. And you click surface view with the Brunel viewer, and you get this kind of results. So this is basically how we use our quality control and statistical analysis and results virtual. We have put all the courses online. You can visit up.course, and up.course we have both English versions and Chinese versions. You can go to see whichever you want to read all the courses, how to use DPAS, how to use DPAP, how to use DPAXer. We also wiki, and we also have the Up Journal Club. Every Friday morning, we will discuss literature in the FMR field. And if you want to join, you can go to online streaming. You can also follow our official account up live. And also, because this Up workshop, this is training in English, and we do not have a hands-on session. If you really need a hands-on session to solve all the errors you encountered, you can go to, in this October, we have a hands-on training session. And this will be continuing. You can just look at up.org to look at what the next on-site hands-on training session is. You can join on that. And also, this is just some follow-up training. And this is one thing is DPAP is very computational intensive. So we know for the surface reconstruction, one subject, one core can be 1 day. So it's important that we have multiple core computers. For example, if you only have one core, then if you have 100 subjects, you need 100 days. And we do have some not too expensive solution. So for the DPI computational core, it can have a parallel computing, and per day it can process 20 subjects. So if you're interested, you can visit deepbrain.com, you have 4, and that can process about 20 subjects a day. So, and this is the WeChat official account of our lab. If you're interested, you can just scan and follow the WeChat account. We will announce the news and the latest journal club will be. And thank you very much. This is my life, and thank you very much for your listening.